Hello, my name is Eric Bartsch. I'm CEO and co-founder of VerdeGo Aero. We are a company that is a leader in hybrid electric propulsion for aircraft and drones, and I'm excited to be here at Oshkosh 2023, standing here in front of a VH3 power plant, which is one of our hybrid electric systems that I'd like to talk about a little bit more to help you understand where this really fits in the market. And it's an exciting capability that's going to lead to many new opportunities for high-performance electric aircraft. VerdeGo was started almost 7 years ago by three co-founders, and we all had about 10 years of experience with electrification. And it was interesting because we had seen a lot of what works, but also what doesn't work. And electrification is an interesting aspect of aviation. It's new, it's revolutionary, it's often misunderstood. There are amazing potentials. There's also amazing hype about things that may or may not obey the laws of physics. And so what's important now is I think we're getting to a point with electrification where we can really see the difference between the things that are really compelling and are going to work and some of the things that perhaps were the earlier ideas that dropped by the wayside, as you have with any revolution in technology. In the early days of VerdeGo, all three founders, we looked at this space and thought, okay, we can apply our knowledge from prior electric aircraft programs that we've done to design a revolutionary aircraft. We started down that path, but we quickly realized that the unique insights that made that aircraft design so compelling were really insights that had to do with how the powertrain worked and the capabilities that you get out of a hybrid electric propulsion system such as the VH3 here. And that leads to the revolutionary capabilities. And so we quickly realized that our biggest value in this market wasn't designing a single aircraft around this power plant. It was designing a family of power plants that could be used in many different aircraft designs, whether that's drones, manned aircraft, unmanned aircraft, military, civilian, you name it. There are hundreds of electric aircraft programs that are active around the world right now, and there are very compelling reasons for needing an aircraft that is fundamentally electric, but that has higher performance than you can get out of batteries. That's where power plants like the VH3 come in. So it was really interesting when we founded the company back in 2017. The three founders who came together was myself, Eric Bartsch. I had a background with battery electric aircraft. I've actually logged flight time in battery electric aircraft in the very early days. Dr. Pat Anderson, who flew the world's first hybrid electric aircraft, is our chief technology officer. And Eric Lindberg, who is that Lindberg, was previously involved with a lot of the early days of encouraging the electric aircraft industry, and before that, came out of the early days in the commercial space flight industry. So Eric, Pat, and I all came together with our combined knowledge of electrification to really look at where we needed to go with the technologies that enable this whole market. And we want to make sure that electrification is not just technically feasible, but it's useful and compelling. And that really led us towards hybridization, where we see that there are huge opportunities for aircraft that have to be powered by electric motors and that fundamentally are different than what we have with conventional aircraft. But those aircraft can't be held back by batteries. And therefore, we need a more energy-dense solution. We need something like the VH3 or the larger power plants that VerdeGo now has under development. And that's really what's gotten us to where we are with the amazing capabilities that are here at Oshkosh. So it's been interesting to see how the horse race among technologies and among propulsion technologies has played out over the last 10 years, because there are people working on hybrid systems, people working on battery systems, people working on hydrogen systems, all different directions. It comes down to having the right tool for the job. And one of the conflicts that's happened many times in this industry is the collision between what I will call aircraft physics and money physics. And aircraft physics, I'm talking about real world physics and all of the engineering principles behind all the great things you see here at the show. There's also money physics, which has to do with what you can get funded. And the fact is that battery electric aircraft were a cool concept. Whether the real physics behind it worked out the way people wanted or not, it was a cool concept to fund. And so often in the early days of a technology revolution, the things that progress the most quickly are the things that the money is flowing to. Those aren't necessarily the things that the physics flows you to. And it's exciting because what we're seeing now is really the money physics and the real physics are starting to align with each other, again, as it typically has happened in the past with other technology revolutions. And people are realizing we need to focus on the things that are going to work and the things that are going to deliver a big impact. And so I would say over the last 9 months, we've seen a dramatic change in how many airframers are talking either openly or behind closed doors about needing hybridization in their aircraft, because they're realizing that the benefits of their aircraft are really driven by electric motors and not batteries. And batteries are the thing that are holding them back the most. And so what they really need is a way of driving those electric motors with a much more energy-dense solution, and that really favors things like the VH3 or the larger power plants in VerdeGo's portfolios. If all we had in aerospace was batteries, and someone invented liquid fuels, we'd be giving them a Nobel Prize, because liquid fuels are 20 times more energy-dense, they get lighter as you use them, the fuel tank doesn't shrink every time you use it, the fuel line doesn't constrict as you're going through the flight, the last drop of fuel is as good as the first drop of fuel. All of those things aren't true about batteries. And it's not that batteries are bad. Every single hybrid powertrain that we put one of these systems in has a battery pack. It's a matter of the right tool for the right job. If you want to store energy on an aircraft, and that's what leads to the range and the performance, you want that in a liquid fuel. And fortunately, there are billions of dollars flowing into the sustainable fuels industry for substitutes for jet fuel, which this system runs on. And so there are ways to make a liquid-fueled power plant very sustainable. But batteries aren't great for energy. Batteries are great for power. If you want a lot of power right now, you want a battery. There's a limit to how much fuel you can flow through this system. And above that limit, you can't run this thing at 3 times its rating. Well, you can run a battery pack at just about any level, and anyone who's been in a Tesla doing an acceleration run knows that electric cars can prove that you can get a huge amount of power out right now if you want it. What we do is we combine liquid fuels and power generation with battery storage so that the batteries take the transient loads. You know, if there is an urgent off-nominal situation, if there's a need for an extra boost in takeoff, if there's a need for an extra boost in hover, those are great use cases for batteries. But when you're cruising along at steady state, if you want any kind of useful range and if you want to comply with energy reserve requirements that the FAA or EASA are going to have, then you need something on board that's converting a liquid fuel into the electricity for that phase of flight. Because we've been fortunate enough to work with several different configurations of hybrid systems and several different prime mover engines inside our hybrid power plants. And so there are several major elements to a hybrid propulsion system. You've got the engine, which in this case is a diesel cycle engine that runs on jet fuel or sustainable fuels. This is an SMA SR305 VDG engine. We just made an announcement with SMA. This is an exclusive version of the SR305 engine that is optimized for hybridization and it's optimized for VerdeGo's needs. So this engine is amazing. It really efficiently converts jet fuel or SAF into mechanical energy. That then flows forward into the generator and the power electronics. We have the cooling systems, we have the control systems, and we have several patents on how all of this architecture is tightly integrated together to give you a system that takes liquid fuels in and puts out electricity very efficiently. So along the way, we've really, as I mentioned, we've optimized this SMA engine, and that gives us outstanding performance and efficiency for the power range of this system, which is 185 kilowatts. We also are working with larger scale engines, including turbine engines, on bigger hybrid power plants. And some of you may know a year ago, actually, at Oshkosh in 2022, we announced that we just closed our most recent financing round, and we're very fortunate to have Raytheon Technologies, the parent company of Pratt & Whitney, as our lead investor in that round. And so we're very excited about the potential to use larger scale engines, out of their portfolio as we go to bigger, higher power levels for different types of aircraft that need to be hybridized. So I think we're at an exciting turning point for a lot of the hybrid electric aircraft programs where now that there is hardware that is accessible, this can be designed into aircraft, but it can also be used for test flights. And so I think over the next year, you're going to see an increasing number of airframes doing test flights, either unmanned or manned, with hybrid electric power plants like VerdeGo's VH3 on board. And then as we get 2 or 3 years in the future, some of those early use cases are going to start to go into production. Now, obviously, anyone who's been in aerospace for a while knows that certification is a marathon. It's not a sprint. That is a long journey. That's no different for electrification. That's no different for hybridization. What's exciting is there are early use cases for unmanned aircraft and for some of the military programs that are letting us build experience earlier on the road to then having these systems fully FAA certified and EASA certified for use in manned aircraft and certified applications. So we're really excited about how all of those things fit together, and we're looking forward to seeing these systems in flight in multiple types of aircraft. Because it's very important when designing an electric aircraft to think about hybridization. Now, I will say that this system is many times lighter than an equivalent battery pack. If you have this system plus a small battery pack plus the fuel, you're anywhere from 5 to 10 times lighter for the same amount of energy than you would be if you had a battery pack. And so 5 to 10 times is a huge advantage in the aerospace industry when it comes to weight. Now, what's important is to design the physical volume on the aircraft so that there is a place to put this system. Whether that's in the tail, whether that's in the nose, whether that's in a pod hanging under the wing, there are lots of different solutions. But I'll tell you, I was talking about the things that weren't as convenient about batteries. I'm now going to flip and talk about something that's really convenient about batteries, and that is that you can kind of squish them into any shape that you want. If you want to have a battery pack that's this tall and really wide, you can have that. If you want to have a cube, you can have that. If you wanted to make a sphere for some reason, you can make that. These components like to be the shape that they are. You can't take a diesel cycle engine and squash it to 1/3 of its width. It doesn't work. So the most important thing to think about early for an airframer who wants to design around hybrids, or maybe they want to design around both batteries and hybrids to protect themselves and have options, is to have a physical volume where this system fits, because this system will be way lighter, I guarantee it, than any battery pack, but you do need to have the right physical space to put this somewhere in the aircraft. The good news is, since electrical power can flow around on wires, you can put it anywhere you want in the aircraft, but it's got to fit somewhere. So we have just recently been able to finally show some of these units out in the public eye, and we've gotten great reception from airframers, really of all types, who are interested in getting much higher performance out of their electric aircraft. And in all of their cases, they have aircraft that have really compelling reasons for needing to be electric. They're designing airplanes that fundamentally can't be built any other way. They have to have arrays of electric motors. They have to benefit from the fast response time of electric motors. There are a lot of great things about electric motors, which are really the big enabling technology in electrification. And so the common thread along all of those is they have to have electric motors in the aircraft, but they've realized that they want to do things with those aircraft and they want to fly missions with those aircraft that are just impossible with batteries. And they're not a little bit off, they're off by 5 times, 10 times, 15 times what they need. That's not just around the corner. That's decades around the corner if it happens at all. they want to get these aircraft in service now. They want to get these capabilities out there now, and that's why they're interested in technologies like the VH3. So the nice thing about hybridization is you can handle reserve energy the same way you handle it with any conventional aircraft. You just put a little extra fuel on board, and fuel is so energy dense that you don't need huge amounts of extra fuel. You're not talking about thousands of pounds of extra fuel the way you would be talking about thousands of pounds of batteries. And one of the paradoxes that we run into in electric flight is that a lot of people designing the early electric aircraft went kind of down the rabbit hole of saying, well, yes, batteries are less energy dense, but maybe I can just focus on really short missions and it'll be okay. The problem with focusing on really short missions is they still have the same energy reserve requirements. Whether it's VFR flight, IFR flight, you've got to deal with weather, you've got to deal with ATC reroutings. And so there isn't really such a thing as a 15-mile long urban air mobility flight, for example, because you probably need 150 miles worth of reserve power on that aircraft to make it legal to take off in commercial service. So these really short flights, you get into this weird design space that we've never been in before, where your reserve energy may be 10 times your mission energy. And that's really problematic. Whereas if you stay in the world of hybridization, you can easily satisfy those requirements because you're talking about a few gallons more fuel, not a few thousand pounds more battery pack. So at Oshkosh this year, at 2023, we're very proud to be included in the U.S. Air Force's AFWERX booth, where AFWERX is really featuring many of the most compelling new technologies in electrification or just in aerospace in general. And they have invited us to display a VH3 because the VH3 has actually been the subject of multiple U.S. Air Force programs funding new technologies and reducing the risk factors on those technologies to accelerate the commercialization. And so we're very happy to be here in the Air Force's AFWERX booth, displaying the VH3 and showing really the potential for applying hybrid technologies like this in a wide array of aircraft programs. And I think it's telling that, the Air Force, unsurprisingly, they first and foremost like new aircraft programs. And if I look around what we're sharing this booth here and sharing this pavilion here at Oshkosh with, it's all aircraft programs except for VerdeGo and except for the VH3. And I think that speaks a lot to how important what VerdeGo is doing is, because without power plants, you can't have aircraft. And that sounds like a silly thing to say, but the reality is anytime you go through a revolution in propulsion, and we've had piston engines, we then have jet engines or turbine engines, electrification is the third major revolution in propulsion that we've gone through as an industry, and we need those power plants, things like the VH3, that give airframers, everyone else in this pavilion, something they can design around and a reliable power source. And so we're very thankful for the Air Force's support and for AFWERX support, and we're very proud to be here showcasing our technologies and how it can enable all of these new aircraft under development. If you're interested in going deeper into this system, go to our website, www.verdegoaero.com. We've got all the specs there. But as you look at this VH3 power plant, what we've done is we've looked at some reference design cases that are kind of generic types of aircraft. And so one of the applications for these systems that's very common is vertical takeoff and landing aircraft, because as an airframer, you can do some really revolutionary things with electric motors that allow you to blur the lines between attitude control, propulsion, reconfiguring the airflow over the aircraft depending on if you're doing horizontal or vertical flight. So there are a lot of really exciting things that you can do with a vertical takeoff aircraft and electrification. Where this comes in is this system, plus a modestly sized fuel tank, plus a small battery pack, all wrapped together as a powertrain. You can configure this so that you've got about 555 kilowatt hours of energy, or more than a half megawatt of energy on board these aircraft. That is way larger than you can ever get on any of these aircraft with a battery pack, because that's the equivalent of 5.5 of the largest Tesla battery packs. So we're talking about thousands and thousands of pounds of battery weight that you can replace with this system that weighs 650 pounds, a battery pack that weighs about 100 pounds onto the side of it, and then let's say 200 pounds of fuel. So all in, you're under 1,000 pounds of total propulsion system, and you're replacing what would be many thousands of pounds of batteries. And that's really the motivation for why you want to put one of these in the aircraft, is all of a sudden you've got way more capability to fly longer missions, faster missions, more payload on your missions, deal with all of the legal reserve energy requirements. It just opens up a whole new world for electric flight that otherwise might be 50 years in the future, if it happens at all. We're seeing diesel cycle engines like the SR-305 get a lot more popular recently in fixed-wing aircraft and conventional applications, and really the driver for that is the extremely high efficiency. One of the really great things about diesel cycle piston engines is you get a much higher efficiency, much lower fuel burn. There are a couple other big benefits, though, that are equally important in the hybrid market. One of those is a diesel cycle engine in aviation doesn't run on diesel fuel, it runs on jet fuel. Jet fuel and diesel fuel are very close cousins of each other, but it's very important to run on jet fuel because avgas is a relatively US-centric phenomenon. You get around the world, you get to global applications, jet fuel is globally available, avgas is not. You also get into military environments. The military stocks jet fuel everywhere because obviously everything the Air Force, the Army, the Marine Corps have, the Navy, they all run on jet fuel. They don't have avgas in all of their locations. So if you want a power plant that can provide power for these electric aircraft, these electric drones, it has to be compatible with jet fuel. And then the final thing that's really compelling about that is there are billions of dollars of research going into sustainable fuel substitutes for jet fuel. And that market is progressing very fast. In fact, those technologies are already certified today. There have been commercial flights with passengers flown in revenue services with those fuels. The big challenge right now is, frankly, getting the supply chain larger and the cost curve down. But that's an inevitability, that we're already on that path. And so these systems have the ability to run sustainable replacements for jet fuel through them, and therefore you've got the sustainability metrics that you would conventionally associate with a battery pack, but you've got the performance that you would associate with conventional engines, and you can get these unique architectures for aircraft that you can't design any other way than to have electric motors. Because hybrid electric systems, are inherently a combination of an aircraft engine, power electronics, generator, cooling systems, and control systems, so that you can convert liquid fuels into electric power. There are also two major subfamilies of the applications of hybridization. You have series hybrid and parallel hybrid applications, and that really has to do with how the airframer applies technologies like the VH3. This system is designed with some patented technology that allows it to be very flexible in how we can install it in different aircraft. So for a series hybrid aircraft, it's a series of technologies that you're stepping through. So you're feeding fuel in series into the engine, which goes into the generator, which makes electricity that goes into the power electronics, which comes out these wires and goes and drives electric motors elsewhere in the aircraft. Now, those things all happen in series, and there are very compelling reasons for wanting to do that. And a lot of these multi-rotor aircraft, that's exactly what they're doing. A parallel hybrid system, the upstream part of that looks similar. So you have fuel coming in, goes into the engine, goes into the generator here, but now some of that comes out the wires. Some of that comes out a shaft that is attached to the front of the generator and can be used to drive a propeller, a rotor, whatever, mechanically on the aircraft. That's a completely different architecture. And in fact, in some cases, what we do then is we run this section of the system backwards. So we can then flow power from the engine through here to the propeller. We can pull some of that off if we need to send it elsewhere in the aircraft on these wires. Or if we want to suck electrical power back into this system and run the generator backwards as a motor, we can boost the power on this shaft and have both the engine and the generator now acting as a motor, putting power out this shaft. So if you think about, for example, a short takeoff and landing application for an aircraft, that's an example of why you might do a parallel hybrid system, because for, let's say, 20 seconds, 30 seconds, a couple minutes, you can run double the power down this shaft that you could otherwise get out of this engine. So you could get amazing acceleration on the runway in a parallel hybrid system, and then switch the electric part of it off and run on this high efficiency diesel engine. So there are a lot of different use cases and a lot of different ways you can apply something like the VH3, whether it's a series hybrid installation or a parallel hybrid installation. We can do both. A lot of people in the early phases of adopting new technologies, in aerospace particularly, obviously looked at, can we retrofit to an existing airframe? Can we put these things on a fixed-wing aircraft, perhaps? And the answer is yes, but we have to be careful because we need the right tool for the right job. And so I'm going to give an example here where turbofan engines are great. We've had them for many decades. They do amazing things. It's a mature technology. Cessna 172s are great. They've been in production for more than 50 years. We still use them. A lot of people get trained in them, even to this date. It's a great aircraft design. Putting a turbofan on a Cessna 172 is not a particularly good idea. You could do it. You could make it fly. I'd probably fly it because it's weird and, okay, that might be interesting, but it would be worse in every way. The payload would be worse. The performance would be worse. The center of gravity would be all wrong. The 172 is optimized around a piston engine. It should have a piston engine. It should not have a turbofan on it. Generally speaking, the best applications for new propulsion technologies are to design an aircraft from the ground up that benefits from that technology. That's why a lot of the things that are being done with electrification look so weird to us, to all of us who've been in this market for decades. It's because when jet aircraft came out in the 50s and 60s, you had all of these swept-wing designs and things that looked like supersonic fighters. Those looked crazy to people who were used to P-51s and DC-3s. That was a crazy new aircraft design, but those were optimized around the capabilities of the jet engine. These new designs that you're seeing with electrification, where you have 6, 8, 10, 20 different propellers on it, electric motors all over the place, those are designs that are enabled because electric motors have unique properties. They're lightweight, they scale differently, they're really reliable, they're very responsive, so all of a sudden you can blur those lines between propulsion, attitude control, active aerodynamics, and do different things. So the best applications for our technologies are always going to be things that fundamentally have to be electric. There will be some corner cases where there is a business case for a retrofit, but that's likely to be a short duration thing, kind of a blip in the market, just as some of the early jet aircraft looked a lot like a conventional piston aircraft. We went through that phase pretty quickly and got to a realization that jet airplanes need to look like jet airplanes. Electric airplanes are going to need to look like electric airplanes.